All right, awesome, awesome. Hello, everyone. It's great to be here. So robotics is a big deal right now, right? There's a ton of hype. There's billions of dollars, but we've had robots for many years. We've had robots since the 70s doing things like building cars. Why is it that right now everyone is so excited about robots? So I think the first question we have to ask ourselves is, what the heck is a robot, right? You've probably seen these things, especially if you live in New York or San Francisco or one of these big urban areas, these little restaurant robots and bartending robots. They'll make you a drink, they'll make you a cup of coffee. So they look like robots, but are they really robots? Or how about this thing? This is a production line which makes cream puffs at some horrendous rate at many millions of calories per hour worth of cream and dough. Is this a robot? Is it cool? Is it something that VCs would invest in? Doesn't really look like it, right? Or what about this thing? This is a Eversys super automatic espresso machine. Its creators are a bunch of crazy Swiss engineers, and they would proudly say that this is a coffee making robot. It's explicitly marketed as an espresso robot. So, in truth, none of these are robots. What they actually are traditional automation setups. These are the systems that have been in the field making money for 50 years, starting with doing things like building cars and manufacturing components for aerospace, now all the way down to things like consumer goods and food. Automation setups are differentiated from modern robotics because they run on rails. You give the system a set of rules, it runs through those rules, it expects everything to be in the same place over and over and over again, 24 hours a day, 7 days a week for 10 years. And that's awesome if you're doing manufacturing, right? If you're manufacturing parts, you want all of those parts to be the same. You want all of those parts to be in the same place and all the time. But it's not really good for a lot of use cases. You wouldn't go buy an automation setup, put it in your house, then like every morning wake up and write a Python program to make lunch. You want something which is a lot more flexible, and that's why robots are cool again. Fundamentally, with advances in AI, with advances in sensing technology, and with some modest advances, but really not driven by the robotics hardware itself, we are able to enable a drastically improved user experience for robots. These user experiences are a lot fuzzier. They can tolerate things being in the wrong place. They can tolerate lighting changing. They can tolerate seeing parts and seeing environments which they've never seen before. So a modern AI native robot perceives the world through sensors, and usually just this means vision. Like there's a lot of other ways to sense, but vision is an incredibly rich modality. You can do it with one camera, you can do it with two cameras, you can do it with four cameras. There are a lot of ways to do it. They follow some sort of natural, easy to give instructions. Once again, realistically, this probably means natural language in 2025. I don't think natural language is strictly necessary. You could go do something like do it with a block-based programming interface, but natural language seems to make sense. Then, based on that prompt and its current environment, it will execute the instructions in a plausible way, right? That's very similar to how if you've ever worked with, say, an image editing model, you can go show like a picture of a person and say, turn this into a frog. And that's not really a sensible prompt, but it'll execute it in a plausible way. And that's the same behavior we want out of robots. Even when there's wild changes in what the training looks like, the robot shouldn't smash into itself, it shouldn't break things, it should behave reasonably or refuse to follow the instructions if they're too nonsensical. And a lot of people ask, like, well, how universal does the robot have to be? The answer really is universal enough to make your business work. There are a lot of people who are doing these universal humanoids, but doesn't have to be a humanoid. As I said earlier on the panel, doesn't have to have legs, one arm, two arms. It's whatever makes things work. So how do we make this happen? The natural way to do it is to sort of like leverage LLMs and break it down like an agent, insert a bunch of object recognition blocks, maybe ask ChatGPT a bunch of times. And you do see a lot of research projects do this, but I would argue this doesn't work. This doesn't work because while the language model is a powerful statistical model that can handle a lot of variation, your rules are not. So the limiting factor is not the underlying model, it's the rules. If you've ever built like a web agent, this is why it's so hard to build a web agent. agent, right? Small changes in the input or unexpected changes in the input will sometimes cause the entire agent to break down. And one of the big problems is you're chaining these discrete steps together. Every step needs to work, and to complete a complicated task, you might need 100 steps. If every one of those steps is a 1% chance of failure, which is pretty damn good if you're doing AI, you're basically guaranteed to fail at the end, and that's a huge problem. It's tough for web agents, and it's basically impossible for robots because you can't have the robot fail even 1% of the time. That means it's physically damaging something in the real world 1 every 100 times. What you really want is this thing they call end-to-end learning, and this is the crux of all modern robotics research. Basically, the idea is we fuse everything. What are the inputs? What are the outputs? The inputs are the sensors. The outputs are what the robot does. Let's learn to predict the outputs from the inputs. And typically, if you dig into the details, what happens is the image data gets embedded by a vision model, typically the vision half of a vision language model, into some sort of vector embedding. And similarly, the prompt gets embedded, usually by the same model, into a vector embedding. These go into this mysterious black box called an action generator, and the action generator learns to predict actions across a horizon, which is to say you show it the past whatever minute, second, 10 seconds of video. It learns to predict the next second's worth of actions. Then you don't go execute that full seconds. You go execute maybe one of those steps, 1/10 of a second. Then you look at the world again and see, like, okay, did the world respond in a way that was expected? And based on that model, you keep on repeating. This core idea of predicting actions across a horizon is what drives everything from modern robotics walking algorithms all the way to these practical task completion things. It gives you a lot of stability because you're averaging the errors across a future, and you can take continued feedback as you execute those actions in order to see whether your predictions were right. So that's the core pipeline that our company services. We're building the tools and the infrastructure to help people scale these models, because these models are really one of the core things that will enable mass adoption of robotics. And with this architecture in mind, if you guys are familiar with AI training, there's a clear thing that you collect, right? The data is pretty clear. You collect the actions out of the robot, you collect the video from around the robot, and then you put those two traces next to each other, and you train a model which predicts the actions from the videos. And as I mentioned on the panel earlier, there's a couple ways to collect the data, and really the crux comes down to what are the predicted actions? Like what is an action? What is an action, right? How do we think about them? So in the simplest, most straightforward case, actions are sensor data collected from real robots. So if you ask a robot to complete a task, it would be things like the forces and angles of the joints in the robot arm, or if it's a gantry, the position of the gantry. Or actions can be these things called latent vectors, these latent actions extracted from video data alone. Basically, the idea is, as you watch a video, you can learn patterns. Even if you don't know that humans have arms, if you watch enough videos of humans doing things with their hands and arms, you learn the pattern that there's this thing that looks like an arm, which will move across the frame to do things, and those correspond to certain changes in the environment. So sensor data collected from real robots is really what the whole industry is based off of right now. As I mentioned in the panel earlier, the reason why people do this is because it forces a mode collapse on the data distribution that makes the models much quicker to converge. It's not really that the exact sensor data is more useful or that the data is higher quality. It's simply this mode collapse. It greatly limits the input distribution, which allows you to converge your model on 10,000 hours of data instead of 10,000 million hours of data, which is what you would have to be if you wanted full coverage of the world. So that's what we're really focused on right now, because it slots neatly into the pipelines of basically every existing AI company. The upside is, of course, is it works really well. It's high quality. It's easy to train on. The downside is you do need an hour of robot time for every hour of data. So that creates a interesting problem or an interesting opportunity, depending on how you think about it. Right? You can have things like staking in robots in order to earn, and I think that's all very interesting too. So this is live today. If you want to go on our platform, you have the opportunity to operate our robot, earn points, join the leaderboards. And The second one, which we recently did a tiny pilot with our friends from Virtuals at, is this idea of collecting just pure video data and extracting the models, extracting the actions from those videos. This is much harder to train on because you have a really broad data distribution and quality is a problem. But really, the upside is you breach through this 1 robot hour per data hour gap, and ultimately you can make things a lot cheaper. And for a decentralized project, it's also useful because you can collect this data passively as you go about your daily lives, which makes it a good fit for a lot of the earning models out there. But the downside is no one is training on this data right now, so you got to wait a little while before you could really make a business out of it. And yeah, that's it. We're growing. We're rolling out more robots. We're rolling out more data modalities. Follow us on X. Visit our website. Tell op your robot today. Thank you very much.